So if you email him, his wife has to read his emails to you. Or him.
What is his age?
Oh,
80s?
probably close to that.
I see.
Okay, so I think we're live now, as far as I can tell.
Yep, I can see that as well.
So it's good that it's working.
Okay. That's good.
I think there's a chat option there in case someone happens to have a question.
I'm gonna test it.
It's working.
That's working? Okay. Okay, hi everyone. We'll start the seminar. I think it's just 2 minutes. So you just joined the spring of 2022. Spring?
Yeah.
Did purposely delay that?
It was COVID delays still during
it was
the
COVID.
yeah.
What course are you teaching this semester?
I do in like the undergraduate lab, the advanced undergraduate lab this semester.
Oh, I see.
It's fun. It takes a lot of time of my Thursday, but it's pretty fun. I think it's an important course. So.
Yes. Cool. I'll try to hold my cough for the introduction part. Okay, I think I will begin now. Hi, everyone. Happy New Year. Welcome to the 117th Online Spintronics Seminar. It's my great pleasure to introduce our speaker today. Dr. Eric Montoya received his PhD from Simon Fraser University with Brett Heinrich and did his postdoc at University of California, Irvine with Professor Ilya Krivoritov. He has been an assistant professor at the University of Utah since spring 2022, where he's building a lab with a focus on magnetic materials and spin physics. So today he will talk to us about the recent findings about the self-generated anomalous Hall spin orbit torque. So without further ado, Eric, please take it from here. Oh, but sorry, by the way, it's the first time we're streaming on YouTube. And if you're watching this on YouTube and if you have any questions, just type into the chat box and we will convey that to Eric after his talk is finished. Sorry for the interruption.
Oh, no worries. Thank you for the introduction and thanks for inviting me to talk about some of our recent work. And thanks again to Kirill and Shin for keeping this Spintronics seminar going. It's a very great service to the community. Okay. So today I'm going to talk about a new spin orbit torque. And And just a bit of motivation. So we're interested in spin orbit torques and spin torques in general, because they allow the electrical manipulation of magnetic materials, basically by using spin currents. You can drive exciting nonlinear dynamics and induce interesting spin textures and things like that. From an application standpoint, you can make non-volatile memory, such as spin torque MRAM, make nanoscale sources of microwave radiation, spin torque oscillators, and both these devices can be incorporated to be utilized for neuromorphic spintronic computing. So yes, today I'm going to talk about a new spin orbit torque that we found that originates from anomalous Hall effects, and also show that this torque is large enough to drive a new type of spin torque oscillator. And I'll also argue that together with the spin Hall torque and the planar Hall torque that have been previously discovered, that this anomalous Hall torque forms a triad of Hall type spin orbit torques that should be universally present in ferromagnetic, non-magnetic material systems based on conductors. Okay, so just spin torques in a nutshell. As I said, we're interested in manipulating magnetization. So the equation of motion is of the magnetization vectors, Landau-Lifshitz-Gilbert equation. Magnetization is an angular momentum, so inherently it's a torque equation, and we're interested in torques. So what's shown here in this cartoon is if we inject a spin current into a ferromagnetic material, so this precessing red vector is meant to illustrate a magnetization vector, precessing about an external field, an effective field. If we inject a spin current, which is these down pointing spins going from left to right, this can exert an anti-damping torque on magnetization. This allows the electrical control of magnetization, as I said. And then owing to magnetoresistance effects, the precessing magnetization leads to resistance oscillations. So dynamic magnetization implies dynamic resistance. And if the source of your spin current is some sort of DC charge current, you have a DC charged current times a dynamic resistance. You have a dynamic spin voltage or dynamic voltage. And large torques can be used to drive magnetization reversal. So that is how you make a memory. These persistent oscillations are how you can drive like a spin torque oscillator type device. So as I mentioned, that these spin Hall effects, the planar Hall effects, and the anomalous Hall effects that lead to torque are they're all intrinsically related. And they're all examples of spin orbit torque. So just as an example, I'd like to use the spin Hall torque or the spin Hall effect as the prototypical example of a spin orbit torque. So spin orbit torques, as an experimentalist, are interesting to me because these are relativistic quantum mechanical effects that you can realize at room temperature on a tabletop apparatus. So for the spin Hall effect, if you have a non-magnetic heavy metal, and by heavy metal, I mean something with a large spin orbit interaction, usually a large atomic number. If you have an electric charge current here illustrated as these spheres, say going from the left to the right, this generates a pure spin current in a transverse direction that flows perpendicular to this charge current. So this is the spin Hall effect. Now, if you put a ferromagnetic material, say iron or permalloy, if it's a metal, yttrium, iron, garnet, it can be a insulator such as that, then this spin current can exert a spin Hall torque that has this form. And working out this double cross product, you can see that where M here is the magnetization direction and P is the direction of the spin current polarization, that this serves to align the magnetization to the polarization of the spin current. So in this case, the spin Hall current is injected into a ferromagnet. This can modify the effective damping in the system, which I call anti-damping, as opposed to using terms like field-like and damping-like. I say anti-damping, but it can contribute positive or negative damping. Okay, so the spin Hall torque can be used to make memory devices. So in a switching device, this is an example of a 3-terminal MRAM device that's been shown. It can drive these persistent auto oscillations to make a spin Hall nano oscillator, of which many types have been shown. It's been shown that these can be phase locked, and these types of oscillators can be entrained to one another, which is useful for neuromorphic computing. So I'd just like to show the symmetry in what I'm going to be showing later is all of our studies are being done in bilayer nanowire geometries. of what these different types of torques look like in these systems. So what I've shown here is the coordinate system that I'll be using throughout the talk. So when I have a nanowire, the X direction is going to be along the length of the nanowire. The Z direction is normal to the surface and the substrate and the film. And the Y direction is just given by like a right-hand rule. Now, all of these spin torques modify our LLG, and they basically have different forms. So the form of the spin Hall torque is given here, where the dependence of the spin Hall torque is given by what's called a spin Hall angle, which characterizes the charge to spin conversion efficiency, the current density flowing in the normal metal. So this is like our spin Hall material, and it's inversely dependent on the thickness of the ferromagnet layer. That's what this DFM is. And so if we have such a geometry and we pass a positive current, what I'm showing as these red and blue spheres is the strength of anti-damping like torque. So for a magnetization pointing in the Y direction, this will lead to a large negative damping. And for under magnetization reversal, this leads to a large positive damping. And as you go away from the Y axis, the strength of this torque dies off. Okay, so that's the spin Hall torque in a very quick nutshell. So I've mentioned that we're interested in these spin torques, and there's effects that we can see due to magnetoresistance. But I'd just like to point out that spin torques and magnetoresistance are intrinsically related. So for each discovered magnetoresistance and spin, there's an associated spin torque that's been discovered, or vice versa. So we had a giant magnetoresistance and tunneling magnetoresistance. A few years later, the associated torque, the spin transfer torque, the first spin transfer torque discovered, well, theoretically predicted, and then discovered. And then the spin Hall torque was discovered, then spin Hall magnetoresistance, and so on. So Rashba torque, Rashba-Edelstein magnetoresistance. And then the oldest known magnetoresistance, the anisotropic magnetoresistance, which is the same effect as the planar Hall effect. The associated torque is the planar Hall torque. So the question is, well, if we consider the anomalous Hall effect to be magnetoresistance-like, the question is there an associated anomalous Hall torque? So that'll be the topic of today's talk. But before I get to that, I would like to just briefly go over the planar Hall torque and the toy model to set up pedagogically how to explain how these anomalous Hall and planar Hall torques work. Okay, so the planar Hall torque is an example of a self-generated torque or a self-induced torque. And that is that this torque acts on the FM that engenders the torque. Another way of saying that is that the spin current that exerts this torque originates in the same ferromagnet that the torque is exerted on. In the case of the planar Hall torque, the spin current, this torque is due to planar Hall currents, which are universally present in FM conductors. I mean, they can be positive, they can be negative, they can be small, so going between them, but they are allowed to be present in all FM conductors. And they can be seen in systems of ferromagnetic normal metal systems with broken inversion symmetry. That's an important point. And so we published this work a couple years back. And to my knowledge, this is the first example of a self-generated torque. And for more info, I point you to a few papers for planar Hall torques and a nice talk given by Chris Safransky in the first year of the Spintronics seminar series. If you look in the archives, you can find that. And then for more on self-generated spin orbit torques, please go see this nice talk by Juan Carlos Rose Sanchez. Okay, so experimentally, what did we see for this planar Hall torque? What I'm showing here in this left panel is measurements in the XY plane. So this is what we call in-plane measurements of torques. And so on the x-axis is the angle phi here, which goes from x to y. And on the y-axis is the change in line with charge current density in the ferromagnet, which characterizes the strength of the torque. Now, for this system, in this system, our ferromagnet was a cobalt nickel superlattice, and our normal metal on the bottom were effective, basically bilayers of tantalum gold, tantalum palladium, and tantalum gold, palladium gold, and platinum gold. And what we saw is that in these in-plane measurements, we saw a torque with the symmetry of the spin Hall torque that followed a sine theta dependence, and it increased with increasing amplitude of spin Hall angle, going from gold to palladium to platinum. So that's just what you would expect for a spin Hall torque. However, when we rotated the magnetization in this YZ plane, here we saw a large spin orbit torque that was out of plane. And most importantly, we saw that the strength of the torque and the angular dependence sign of the torque didn't depend on the this underlayer. So it was roughly the same for gold, palladium, and platinum. So when we saw this, we thought that this can't be due to the only due to the adjacent normal metal. It has to be something going on in the ferromagnet. Okay, so the magnitude of the planar Hall torque was not strongly dependent on the adjacent normal metal. So we decided to introduce a toy model, and the starting point of that is basically the planar Hall current. So in a ferromagnetic conductor, the spin-orbit interaction gives rise to magnetization-dependent spin-polarized electric current. The magnitude depends on the direction of the magnetization. It flows parallel to the magnetization, as shown in this cartoon here. It's polarized parallel to the magnetization, and this effect is what gives rise to AMR and the planar Hall effect. And we can call this the planar Hall current. And it follows this form. It depends on the AMR ratio, if you will, and the projection of the magnetization onto the current direction, and it flows in the M direction. So the simple equation is just basically the mathematical realization of these bullet points. Now, what we did is we introduced a toy model that if we have a spin current that's generated in our ferromagnet, if we put an adjacent normal metal, then we can have spin transfer between the ferromagnet and the normal metal that goes across this interface. And in our geometry, this interface is in the Z direction. So if you just take the component that goes across this interface, this is simply the planar Hall current projected onto the Z axis. And if you work out this, it has this angular form, which can be described like by this equation here, this cosine theta, sine theta, cosine phi. And this is exactly the angular dependence that we're showing as these solid lines that we're fitting to the data. So the angular dependence of this torque that we saw followed the Z component of the planar Hall current. And that's the component that goes across the interface. Now, the next thing that we had to argue is that, well, what is this? So we have this transfer of spin angular momentum. What else is necessary? So in the steady state, we can't have a net charge flow across this interface. This is another way of saying we can't have infinite charge accumulation. So this implies that we have to have a backflow charge current. Now, to maximize the spin transfer across this interface, this backflow spin current, or this backflow charge current, must be unspin polarized. So the adjacent normal metal must be a good spin sink or a good spin scatterer. Okay, so to show that pictorially, if we have a ferromagnet that's embedded between two normal metal layers, there needs to be a spin scattering asymmetry between the two normal metals. So one of the layers must be a good spin sink, as I'm showing in red, and one of the layers must be a poor spin sink. Another way, this is just another way of saying we need broken inversion symmetry. Otherwise, the net spin transfer across to the FM is 0. So in the case where you have, say, a good spin sink on the bottom, a poor spin sink on the top, you would expect a large planar Hall torque. If you have a good spin sink on both sides, you have efficient spin transfer at both interfaces. However, they're opposite signs and they compensate each other. So you would expect to see no planar Hall torque in such a system. And if you have poor spin sinks on either side, then you have no net spin transfer at all, and you would also expect to see no planar Hall torque. So then we did a series of experiments where we took the structure that we had. In these cobalt tantalum, what we found was interesting for the cobalt tantalum interface. This had a 0 spin mixing conductance in our system, and the tantalum on its own acted as a poor spin sink. However, with the insertion of a gold layer, the net layer turned into a good spin sink. we could actually put another gold insertion layer on the top layer, and then we had 2 good spin sinks, and this actually turned off this planar Hall torque effect. And then finally, we placed this tantalum layer with an aluminum oxide, which is this gold aluminum oxide layer is a pore spin sink, and we recovered a large planar Hall torque. So these experiments show that the planar Hall torque is not purely interfacial. There's a non-local locality involved. The spin current needs to be absorbed somewhere, but it's not happening right at the interface. So it's not due to some effect such as spin memory loss right at the interface or a Rashba-like torque directly at the interface. And so the planar Hall torque actually has this this interesting symmetry. So again, this is showing for a similar to the spin Hall angle, a planar Hall torque angle. With a positive planar Hall torque angle, it would have this type of symmetry. What's interesting is that it's large in this XZ plane. It's a large torque out of plane, which is different than, say, spin Hall torque and Rashba torque. And it actually shows 4 extrema in rotation under 360 degrees. And what's very interesting is that it's actually even under magnetization reversal. So if you reverse the magnetization, the torque doesn't change its sign. It's actually rotation by roughly 90 degrees. And so this is the full form that you can find in this paper of the planar Hall torque that goes beyond our toy model. Written into this form, we've translated it into what to us is more experimentally accessible parameters. You can see in our recent archive paper. But this torque can actually be added, just like the spin Hall torque, into a micro magnetic or even a macro spin LLG solver, if you are interested in studying these types of dynamics. Okay, so as I showed, the spin Hall effect leads to these transverse spin of polarized currents. The planar Hall torque or planar Hall effect also leads to these transverse spin polarized currents. These transverse spin polarized currents, when going across an FM-NM interface, can lead to torques. So the question is, well, can the anomalous Hall effect lead to a torque? And it's known that the anomalous Hall effect leads to transverse spin Hall currents. And it's been theoretically predicted that the anomalous Hall current can exert a spin transfer torque on another ferromagnet, which was shown just a few later. This was experimentally realized. But the question that we were asking is there a self-generated spin orbit torque associated with the anomalous Hall effect? So this is essentially generating a spin current using the anomalous Hall effect, but it's still a spin transfer torque. So what we're looking for is a little is different. We're looking for a self-generated spin orbit torque. Okay, so as an experimentalist, one of the first things I ask myself is, what material system should we use to look for such an effect? And so we went to this quite useful paper by McGuire and Potter that goes over magnetoresistance effects in various metallic alloys, ferromagnetic metallic alloys. And you can see that it's quite well known that nickel iron alloys, so the most famous would be permalloy, this nickel 80 iron 20 concentration. However, if we change the nickel iron concentration, we can tune the anomalous Hall effect quite strongly with the nickel concentration. So, and it has a very strong anomalous Hall effect that can go from positive to negative. Furthermore, it's been shown that even within the same alloy concentration, that by using growth morphology, so this is not what we'll be doing in this studies, but we can think to the future, is we can actually, with disorder, we can change the strength and even sign of anomalous Hall effects in these alloys. Okay, so the idea is we wanted to choose a material system where we can significantly tune the anomalous Hall effect. So here's just a cartoon of our heterostructure design. We start with a sapphire substrate. We use as our spin sinking layer, we again use this gold tantalum bilayer. The tantalum is an efficient spin scatterer, so it acts as a sink. It's highly resistive. That's important because the self-spin orbit torque is proportional to current densities flowing within the ferromagnetic material. So we don't want our adjacent non-magnetic materials to be shunting all of our current. It'll reduce our effects. And also the tantalum grows amorphous nanocrystalline. This leads to very smooth films, promotes good growth, and this leads to sharp interfaces. We use the gold layer again. This is playing two roles, so it has a good spin mixing conductance. If it's very thin, not too much bias current goes through it, we're actually going to use this as a strip line for FMR. So this gold layer will always provide an Ørsted field. So as I'm going to show, our measurements are going to be spin torque ferromagnetic resonance measurements, where if you have small spin torques, you're not going to see much signal. So if you always have an Ørsted field, you can measure this, what's called SDFMR, but it's more analogous to, say, just strip line FMR. And then we use these nickel iron layers. We keep these at 5 nanometers. The reason 5 nanometers is just a compromise that it's thick enough to give us a good ferromagnetic response. However, the spin torques are interfacial effects, but they're not purely at the interface, but they should follow a 1 over the thickness of the ferromagnet, as I'm illustrating by DFM here. And then the aluminum oxide is just an insulating capping layer, which is a pore spin sink. So in these devices, we have a pore spin sink on the top. We have a good spin sink on the bottom. So the first thing we do is we make Hall bars so that we can quantify the anomalous Hall charge effects. And I'm using the term charge here. This is just what you would typically just call anomalous Hall effects, because there are spin counterparts. And just to keep things straight, I'm going to try to remember to say charge whenever it's what you would call the normal anomalous Hall effect. So we measure the anomalous Hall resistivity in these samples, and we see that, in fact, that we have a large anomalous Hall resistivity that's tunable by the nickel alloy concentration, which is shown on the x-axis here, anomalous Hall charge resistivity on the y-axis, and it follows a similar dependence that we expect from film type measurements. Furthermore, we measure the longitudinal charge resistivity in these samples. It follows a dependence like this. And we can take the ratio of the anomalous Hall charge resistivity, which is the transverse resistivity, to the longitudinal resistivity, and define what's typically in the literature called an anomalous Hall angle. And I'll try to call that the anomalous Hall charge angle. And that's basically the ratio of the anomalous Hall charge resistivity to the longitudinal resistivity. So we, in fact, can tune in these systems this anomalous Hall charge effect. What we then do is we make nanowire devices using e-beam lithography and ion mill etching techniques. And these nanowires are, we start with our film, and then we pattern these into 56 nanometer by 30 micron long nanowires, and then we attach leads and subsequent deposition and liftoff process to define an active region that's on the order of 100 to 350 nanometers. And then when we apply currents or microwave currents or DC currents, the current densities are only large within this active region, and that's where our signal is going to come from, whether it's magnetoresistance, spin torque FMR, and what will show microwave emission. So all of our signal is coming from what's shown in false color here as this blue, that's our nanowire. So the main characterization technique we're using is is spin torque ferromagnetic resonance. And as I said before, this is actually a combination of spin torque drive and Ørsted field drive. So in this system, we inject microwave current across the RF port of a bias T directly into our sample. And then under either Ørsted or spin torque drive, we have dynamic magnetoresistance that's at the same frequency as this microwave drive. And this makes a rectified voltage. So we have basically, say, cosine squared. This gives us a DC component that we can measure along the low frequency arm of a bias T. And then we're going to also use field modulation so that we can use phase sensitive detection to enhance our signal to noise ratio. And what we're going to do is we also apply a DC bias to the sample so that under spin torques, we have this charge to spin current conversion. Okay, so what's shown on the right is the typical spin wave eigenmode spectra. So shown on the x-axis is the applied magnetic field. And in this case, it's applied at this angle of 330 degrees. So this is in this YZ plane. And so it's out of plane. measurements. And I just note that the range is clipped here on the vmix, or this SDFMR signal, to illustrate that we actually have these higher order modes. And what we're going to do is we're going to look at the dynamics of this lowest order spin wave mode. I've labeled spin wave 1 as a function of DC bias. Okay, so what does that look like? Okay, so here's a trace. So this is basically, we take this 3-dimensional parameter space and we take a slice of it to make this 2-dimensional parameter space, where now the x-axis is the applied magnetic field, and the y-axis is our SDFMR response. And we see that we have these 3 spin wave modes that we can resolve. And we're going to look at this highest field spin wave mode. We're going to look at its line width as a function of DC bias, because the line width is proportional to the damping. And an anti-damping torque changes the damping with applied, say, DC current. Okay, so when we apply one current density, say positive 1 milliamps, we see that there's actually a widening of the spin wave mode. And when we apply the opposite current density, there's a narrowing of the spin wave mode. Now we're out of plane, and so there's also contributions to the amplitude of these signals due to basically photovoltage effects. Okay, so then what we do is we vary the bias current at a fixed angle, and we track what is happening to the line width. And so again, the line width is proportional to the damping. And so we see that we have a linear dependence of the line width on the damping, the slope of which characterizes the strength of the torque. And then what we do is we basically vary the angle of the applied field, and the angular dependence gives us the symmetry of the torque. So this is shown that the torque changes sign under magnet. This is a rotation by 180 degrees, or magnetization reversal. Okay, so shown here for this nickel 70 iron sample is what the slope of the line width versus bias current as a function of angle. And we see that we have a large torque with novel symmetry. We have some small contribution in the XY plane. So when we're at 90 degrees, this is along the y-axis. We attribute that to the spin Hall torque in the tantalum gold underlayer, which in the previous planar Hall torque data I showed, this is a very small contribution. However, we see a large out-of-plane contribution. So here, these values are large. That's large in this YZ plane. And just to point out that the planar Hall torque had a large component in this XZ plane. So this is this torque that we're seeing here is large in this plane as we vary this. So for basically phi is set to 90, and we rotate this angle here, whereas the planar Hall torque is phi is equal to 0, and then we rotate the theta. And this is well described by theoretical prediction for anomalous Hall torque induced angular dependent line width. That should follow this form. So you can find more details in this paper here. And so this is saying that the expected change in line width with applied current density is given by what's called this AYZ. This is the anomalous Hall torque damping efficiency times this angular dependence here, which is there's a sine theta term and a sine 3 theta term. And I just want to point out that this is not an expansion in terms of odd powers of sine theta, because you can see that the amplitude is equal. So that's important. And then there's the sine phi term. So then what we do is we do the similar measurement for all of our nickel iron alloys, which is shown here. And we see that with increasing nickel concentration, that the strength of our torque increases. So the torque has a clear dependence on the alloy concentration. However, what was unexpected to us at one point was that it didn't change sign, which I showed you that this anomalous Hall effect, so this what I'm calling the anomalous Hall charge effect, does change sign. So this at first was a mystery, which I'll hopefully in the subsequent slides I'll explain. But I want to show one more piece of experimental evidence. So we want to look at microwave emission. So we make essentially a spin torque nano oscillator. Now, for these devices, we remove the gold insertion layer. We find that the nickel iron tantalum interface has a good spin mixing conductance from broadband FMR studies. And the tantalum layer acts as a good sink. The reason we removed this gold layer is that this was shunting some of our current, and we want the current to mostly go through the FM, the ferromagnet, if the spin orbit torque is due to spin currents induced in the ferromagnet. And then we just need this spin sinking asymmetry, which this device satisfies. So the spin torque FMR is much harder to measure in the system, but what we're going to do is a microwave emission measurement, which is a different type of measurement, and we don't need that gold layer to act as a strip line. And I just point out that the next measurements are all done at 77 Kelvin because we are applying large current densities and we have large heating. I forgot to mention the previous measurements are all done at room temperature. Okay, so shown here on the right is a schematic of the experiment. So we just put a DC current, we apply a DC current to our nanowire through the low frequency arm of a bias T. This drives, when we have a large spin torque, this drives the magnetization dynamics. Again, magnetization dynamics and magnetoresistance leads to resistance dynamics. So we have a DC current and microwave resistance oscillations, which gives us a microwave voltage that we can detect with a spectrum analyzer. And so the microwave emission is shown here on the left, where on the x-axis, I'm plotting the applied DC current, and the y-axis is the frequency of microwave emission, and then encoded in the color is the power spectral density of the emission. And what's shown here is the spectra that's observed with the magnetization pointed in this direction. And for the positive current polarity, we see a coherent microwave emission. And just to point out, so this is at this 145 degrees, which is near the maximum of where we expect to see an anti-damping torque. So the change in line width is negative with applied DC current. So we have negative damping for positive applied current. We're putting a lot of current density through these nanowires. So actually for the negative current polarity, we see what's essentially mag noise or thermally driven fluctuations that we can resolve. However, their output power is much smaller. And also you can see that there's a much larger nonlinear frequency redshift for the coherent microwave emission, which are both signatures of what you expect for auto-oscillatory behavior and not just only mag noise. Now, according to this symmetry, under magnetization reversal, we would expect the torque to change sign, and that's exactly what we observe. So when we rotate the magnetization by 180 degrees, we see that the sign of the torque changes. So now for positive current, it's additional damping, and for negative current, this is anti-damp. Okay, so I've shown you experimentally what we see, and now I would like to spend the rest of the talk trying to convince you that this is in fact due to anomalous Hall effects. Okay, so what is the origin of the spin orbit torque? Well, the charge current density in the ferromagnet. So what I'm showing here is a cross section in this the YZ plane up here of our nanowire. So if we have charge current density flowing in the X direction, that's kind of out of the board or out of your screen, shown here as this plus JFM. This leads to a transverse anomalous Hall spin current that we call QZ. The magnitude depends on the FM band structure, and the direction of the spin current or magnetic moment is collinear with the spin momentum that it carries. So we call this the anomalous Hall spin current because it's essentially the spin sector analog of the anomalous Hall charge current shown here. So this is the typical anomalous Hall effect current that you would measure, or that you're probably more familiar with. So this anomalous Hall spin angle is basically the spin sector analog of this anomalous Hall charge angle like shown before. Okay, so in the literature, this anomalous Hall spin angle is usually broken down into two components, which is the more well-known anomalous or spin anomalous Hall effect angle, or the spin Hall angle, and what's called the spin anomalous Hall angle. Now the thing is, these have the same symmetry, so that we are only sensitive to the algebraic sum of these two torques. So in an infinite ferromagnet, this anomalous Hall spin angle characterizes the anomalous Hall spin current totally. However, in our nanowire device, or in basically any sample, we aren't an infinite ferromagnet, and that does have a consequence. So, and that's due to this anomalous Hall charge current. So this anomalous Hall charge, this charge current leads to this well-known charge accumulation in a finite sample. And this is what we call the anomalous Hall effect. So it has this symmetry where you can see this in our geometry. This my comes from the fact that this goes as like an m cross e. So we're looking at, if we have a z direction, this is given by this m cross e, that's the e field and the magnetization that's usually for the anomalous Hall effect. Now, again, similar to our toy model that I explained before for the planar Hall effect, is that we can't keep accumulating charge. We can't have infinite charge accumulation. So in the steady state, this means that this charge accumulation needs to drive a counterflow charge current. So this counterflow current is just given by the, basically it goes in the opposite direction and has equal magnitude to the anomalous Hall charge current. Now, this backflow charge current is a longitudinal transport in a ferromagnet. So this charge current is then polarized with its direction and magnitude of the spin current density is given by the intrinsic polarization that's usually written down as P, that takes on values between -1 and 1. And that's of the ferromagnet. So the net effect of this anomalous Hall charge current in a finite sample is that it leads to this backflow of spin current density that's given by this equation here, where this P is the polarization and this this is the anomalous Hall charge angle, which is what in the literature is usually just called the anomalous Hall angle. This is the transverse resistivity over the longitudinal resistivity. Okay, so this net spin current that we have is just given by the sum of the spin current densities arising from the spin anomalous Hall effect and the spin Hall effect, which we're calling the anomalous Hall spin currents, and this backflow spin current. And just to note, in our geometry, my is not the direction my is not given by nothing other than just sine theta sine phi. And so we can collect these terms, and so we see that we have this charge to spin. We're governed by this charge to spin conversion efficiency, and just an intrinsic spin efficiency. So how does this lead to a torque? Well, again, we need to assume, or we need to have asymmetric spin current sinks on the top and the bottom. So shown here, for a device like ours, we assume we have a large spin accumulation, US, at the interface when we have a poor spin sink, so we can't efficiently scatter these spins. In our case, that's at the top. And we have negligible spin accumulation at the interface with a good spin sink. So in our case, that's at the bottom. So we have some spin accumulation that looks like this. That's shown here. Okay. And then furthermore, when you have the conversion efficiency of such a spin accumulation into current-induced damping actually goes as the mz projection squared, or it has a cosine squared theta dependence. And that's actually worked out in this paper here as well. And then if we assume maximum efficiency of this conversion of this net spin current or spin accumulation to a damping, it has a form like this. Okay, and so it's inversely dependent on the magnetization and the thickness of the ferromagnet. It's proportional to what we're calling the total anomalous Hall torque angle. It's proportional to the charge current density in the ferromagnet, and then it has this cosine squared sine theta sine phi term. And this term here that this form that we've seen here. just noting that this trig identity, if we can turn this cosine squared theta, sine theta can be written as 1/4 sine theta plus sine 3 theta. And then putting these two equations together, we can see that this efficiency of these anomalous Hall torques to create anti-damping effects or to change the line width is given by something like this. So we have constants. It's just directly proportional to the anomalous Hall torque angle, inversely proportional to the saturation, magnetization, and the thickness of the ferromagnet. I just point out that this getting to this equation, we're neglecting things like anisotropy and things like that. Okay, so we can convert our the data that we directly measured to this AYZ just using this equation. So this efficiency looks like this. Okay, so this is what our experimental result would be. And then on the right, we're gonna try to calculate what we'd expect for AYZ as a function of the nickel alloy concentration. Well, I already showed that we measure this anomalous Hall charge angle. This is essentially this anomalous Hall angle. This is the transverse resistivity, charge resistivity over the longitudinal charge resistivity. We estimate the polarization. We can't directly measure it from literature values for such systems. And then for this anomalous Hall spin angle, we don't know of any experiment where this has been measured. However, we can estimate it from our experimental for ferromagnetic metal conductivity and calculated values of the transverse spin conductivity for nickel and iron, which were reported in this very nice paper here. And we interpolate between these values between nickel and iron, and we interpolate between the polarization, and we use that in conjunction with our experimental data, we calculate a dependence that looks like this. And I just want to point out that this is a calculation. There's no fit parameters. And what's interesting, importantly, this shows that not only do we qualitatively capture the dependence, is that we actually capture the correct sign from theory, and we also capture even the right magnitude, not even just order of magnitude. The magnitude that we calculate is strikingly close. And now, so this